We're going to look at another example of using the divide and conquer paradigm in order to solve some problem. And we're going to see our problem today is integer multiplication. So the idea is that we have two integers, I and j. Each are represented by an n bit string. So we've got n bits associated with each integer. Now, in order to multiply them, one way that we have just kind of straightforwardly is to, at least this is how I learned it in grade school. I'm not sure how they've changed it since then. But if we wanted to multiply these together, we could just take C1 and multiply this with B1, get our result, multiply it with B2, get some result we'll store here, and then B3, and then each one of these all the way up until n in order to get n results. And then repeat the same process but with C2 and kind of shift over everything. So we've got C2 times B1, C2 times B2, and so forth. And then we would do that n times, once for each of the n bits that we have in J. So we would have a few bit strings, exactly n bit strings here, and then once we get all of them, we would add them all together in order to get our resulting I times j bit string. Now, if you didn't learn it this way in grade school, that's okay. The way in which we go about this isn't super important. I just wanted to remark that in doing so, we get a big O of n squared running time. And this is because we have, in this case, n additions that we have to make, and each addition has n bits in it. Okay, so if we were to just multiply these together, we get big O n squared runtime. We're going to see, though, how we can do this using divide and conquer. That's the purpose of this topic. How would we use that divide and conquer paradigm in order to solve this problem? So we need a way to divide our original input into smaller sized subproblems. So we're going to split our bit string into higher and lower order bits. So we've got IH is a bit string of size n over 2, and IL is a bit string of size n over 2. So you can imagine this as if this was that entire bit string represented by I. So we've got all the higher order bits here and the lower order bits here. We just cut it in half. And now we'll use IH is the first n over 2 bits, and IL is the second n over 2 bits, the lower order bits. And we do the same thing for J. Now, if we want to give in the higher order bits just by themselves and the lower order bits by themselves, we want to reconstruct our original bit string, then we would take whatever our lower order bits are and then add them together with our higher order bits offset by n over 2. And this is our equation here. So I is equal to our higher order bits offset by n over 2 bits. So we're multiplying it with 2 to the power of n over 2. That will effectively shift if we're given our higher order bits here. We're just going to shift them over so that they're in this position, so we can add together our higher order bits, this resulting shifted higher order bits with our lower order bits. And this gives us our original bit string. So we have a way of breaking up our input into smaller sized inputs. Now we can define, we want to find what I times j is, and we can do that by just using substitution, what we've redefined I and j as. So we have I times j is equal to, we know this is what I is equal to, and this is what j is equal to. This is just our higher and lower order bit strings corresponding to I and j. And then from there, we can just multiply these out, use the FOIL method. So we multiply our first terms, we multiply these terms together, we multiply these terms together, and then we multiply the last terms together, FOIL. Okay? So this is how we would get the following. So we've got now, if we want to multiply I times j, we can break up I and j into higher and lower order bits, represented by H subindex and L subindex. And in order to compute this, we actually just have to compute this summation here. Now, in order to calculate this, we have to solve multiplying these smaller terms together, these smaller terms together, these ones, and these ones. So we have 4 subproblems now, and each of these will be a recursive call to our algorithm to multiply 2 integers together. But now we're multiplying 2 smaller sized integers together. So those will be the number of subproblems, and our subproblem here is now of half the size of our original problem because we broke up each bit string in half. And then we also have some non-recursive overhead, and this comes in the form of we have bit shifts, where we're multiplying by some power of 2 to shift these bits over. And then we also have additions. But bit shifts, integer addition, and integer subtraction using an n-bit string is linear time. So if we're just shifting over, let's say, n positions, given whatever our result is here, if we want to shift this over n positions, we'll just add n zeros to the nth bit. If we want to add together 2 n-bit strings, maybe here's one n-bit string and here's another n-bit string, then we just have to go through each of the n positions and add them together. So those operations, bit shifts, additions, and even subtractions, we can do these in linear time. So that means that we have now 4 subproblems, because we have to compute this first, second, third, and fourth term. So we've got 4 subproblems, but each of our subproblems now are of size n over 2, because we broke our bit string in half. And we have a linear amount of non-recursive overhead, and this overhead is coming from doing bit shifts and adding bit strings together. So this is essentially everything other than what we computed recursively. So this is how we would, in our conquer step, take the solutions to these 4 subproblems and then use them in order to give us a solution for our original sized input. So we can use the master theorem to figure out what the running time of this would be, since we have this recurrence relation. And remember, from the master theorem, we have to compute what is our non-recursive overhead, which is n, and then compare this to a critical function, which I'm going to write on the side here, n to the power of log base b of a, and here b is 2 and a is 4, which is n squared. And the master theorem will compare these 2 functions, figure out which one is polynomially smaller or larger if they're equal up to some logarithmic power, and give us the running time. Now in this case, our critical function is the fastest growing function, so our running time is big theta of this faster growing function, which is n squared. But this isn't any better than what we had before if we were to just straightforwardly apply what we, or at least what I learned in grade school. However, we know that the runtime of this algorithm is dictated by our critical function, because this was the faster growing function. And our critical function, whatever this value is dependent on b and a. The size of our subproblems, n over this number, and the number of subproblems that we have. So if we can reduce this power, we will have a faster algorithm. And it turns out we can do that by decreasing the number of subproblems that we need using just some algebraic manipulation. Now we're going to use this same equality in the next slide. We're going to figure out an even better way than this one to multiply 2 integers together. And we can factor out here, for example, this 2 to the power of n over 2. So we've got here the higher order bits of both I and j times 2 to the power of n, and then the higher and lower order bits of each one, respectively, added together. And then we're just factoring out 2 to the power of n over 2. I'm writing this down because we're going to use it again in the next slide, and this is where it's coming from. So we're going to reuse this. We already showed that these 2 things are equal, so if we can figure out how to compute this summation using less terms, having to make less recursive calls, by computing this summation, we will effectively be computing what the result of I times j is. So we're going to work with this summation now. And we're going to try and improve this so that we can multiply two integers in less than n squared time. So our approach is still the same, to divide our input into smaller sized inputs. So we take whatever our bit string, let's say I is, and we break it up into, here are the n over 2 higher order bits of I, and here are the n over 2 lower order bits of I, and we do the same thing for j. And as we saw in the previous slide, we know that this summation is equal to I times j. So if we can solve this summation, we'll already have our result I times j. And we'll see how the top two equalities come into play here in a moment. Now, before we get to that, though, I want to show you the product of the following term. Now, this might seem kind of weird to consider at first, but we'll see how we can use this moving forward. So let's take the higher order bits of I minus the lower order bits of I times the lower order bits of j minus the higher order bits of j. And we'll multiply this out. Again, just using the FOIL method, multiply the first terms together, plus the outer terms multiplied together, plus the inner terms, plus the last terms. And we get the higher order bits of I times the lower order bits of j minus the higher order bits of I times the higher order bits of j minus the lower order bits of them both plus the lower order bits of I times the higher order bits of j. Okay, now that we're given this, we're going to put the higher order bits of I and the lower order bits of j. So we're going to put this on the other side, on one side, as well as the lower order bits of I and the higher order bits of j. So we're going to keep these two terms just on one side, right? So we're basically going to take these negative terms and put them on the other side. That way we have on one side only these two terms here. So let's rewrite that. Once we've got now the same sum that we had here on the left side, the product, and we're going to add to both sides IH times JH and IL times J. So we've got this term plus this term, which is equal to, since we've canceled these out, we're left only with the following: IH JL plus IL JH. Okay, so why did we do this really? We're going to use this and substitute. Notice that this side that we have here is exactly what we've got in parentheses here. So we can substitute this summation with everything that we figured out. This is equal to everything on the left. This is how we get the following. So we have here everything in brackets is what we figured out this is equal to. This product, our higher order bits of I minus lower order bits of I times lower order bits of j minus higher order bits of j plus the higher and lower terms of I and j combined. Okay, so why was that so important? Why did we have to do that really? We used some kind of algebraic manipulation here, a trick to figure out this summation is equal to something else instead, but why would we want to use this one instead? Alright, I'm going to erase everything so we can see why this is so important. So now we know if we want to compute I times j, all we have to do is compute everything which is on the right. And as it turns out, this is a better way to go about it because we have less terms. This looks like more, but let's see what our common terms are. We have the higher order bits of both I and j, which we use twice. So we only have to compute it once, and then we can reuse it again. And we've got the lower order bits of I and j, which we also have twice. So far these are 2 subproblems. And then we have this term here that we have to compute. Now, in order to compute this, we have to first figure out what IH minus IL is. That's a linear time operation, so we've got some half-size bit string times another half-size bit string that will compute JL minus JH. But remember, we can do bit strings, addition or subtraction in total linear time. So we've got 1, 2 subtractions, 1, 2 bit shifts to make, and then 1, 2, 3, 4 additions. So this is still a constant number of times that we're going to call a linear time operation. So we've got a total of 3 subproblems. This was our first, second, and third subproblem. We repeat that subproblem here as the same first one. We don't have to do it twice, and the same third one. So we've only got 3 subproblems. They're each of size n over 2, and we still have a linear amount of non-recursive overhead. This is coming from our bit shifts, addition, or subtraction. And according to our master theorem, we just have to figure out which case we're in. So we've got our non-recursive overhead, which is n, and we'll compare this to our critical function, which is n to the power of log base 2 of 3. And take whichever one of these is larger. So here we've got n to the first power, and if we compute log base 2 of 3, this is roughly 1.585. And between them, we take whichever one is polynomially larger. So in this case, our total running time is big O, big theta of n to the power of log base 2 of 3, although this value isn't any more than 1.585. So we got a better running time. Before we could only do n squared, and now we have something which is even better. I don't claim that this is the best possible way that we can multiply integers together, but this is a good example of how we can use a divide and conquer algorithm to incrementally improve the running time of some algorithm. You notice that we were able to improve this by reducing the number of subproblems that we had. And why that's so important is we showed using the master theorem that our runtime is really based on these things: the number of subproblems, the size of each subproblem, and our non-recursive overhead.